So we're going to start Algebra 2 Honors by talking about all the different parent functions that we will be using this semester. So you should have a copy of your little parent functions booklet. And we'll begin with the constant function, which is the most simplest of the functions. The equation for the parent constant function is f of x equals c. We use the letter c to represent a constant, which is just a number. There's no x in the equation. So for the example constant function, I have picked 4 to be our constant. So this is for y equals 4. And what that means is when y is 4, well, it doesn't matter what x is. So x could be -3, -1, 0. I'm just thinking of random. It doesn't matter what x is. Y is always going to be 4. And if we plot these points on our coordinate plane, we have -3, 4. And I'm thinking that some of you may remember what's going to happen here when you have y equals some number, what kind of line we're going to have, what kind of slope we have. So let's keep graphing. -1, 4, 0, 4, 1, 4, and 3, 4. And if we connect our dots or points, we have a horizontal line with a slope of 0, which makes sense because 0 times x makes it go away. So a constant function is always going to be a horizontal line. Okay, so now we're looking for an x-intercept. And if you've forgotten, x-intercept is where our graph crosses the x-axis. And as you can see, it does not, so there is no x-intercept. The y-intercept is where the line or graph crosses the y-axis, and it crosses right there at 4. So the y-intercept is at 0, 4. And let's come over here to domain and range. That's something you've discussed before. So domain is all the x values and range is all the y values. So domain, we're looking from left to right. If we see that it goes to the left forever, and if we follow the line to the right, we see that it goes to the right forever. So there's 2 ways that you can write the domain and range. We have set notation, and for our set notation for domain, it is the set of all real numbers because it's everything. It goes forever in both directions. We also have interval notation. So interval notation would be it goes to the left all the way to -infinity. It goes to the right forever to positive infinity. And infinity isn't actually a number, so we use parentheses around that interval. So if we look at the range, well, how far down does it go and how far up? Our y values go up and down. So how far down does it go? 4. How far up does it go? 4. So in set notation, our range is 4. And in interval notation, from 4 to 4. Notice this time we used square brackets because 4 is an actual point on our graph. Okay, now let's talk about end behavior. So when we're talking about the end behavior, we're talking about the ends. What's happening when it goes to the left? What's happening when it goes to the right? So as x goes to -infinity, what is y doing? We want to know that. And as x goes to positive infinity, what is y doing? So x going to -infinity is the left. Negative is in the left direction. So as x is going in the left, where is the y? The y is still at 4. And then as x is going in the positive direction, so positive numbers are on the right. So as the line is going to the right, what is the y doing? It's still at 4. Doesn't go anywhere else. So that's the end behavior for a constant function, or this constant function. Okay, next function is the linear function. Another one you guys should be very familiar with. So the basic parent function is y, or f of x, equals x. So nothing's added or multiplied or anything with it. It's just plain x. So if we plug -2 in for x, what's y going to be? -2. If we plug -1 in for x, what's y going to be? -1. And hopefully you get the pattern. Y is equal to x, so it's always the same thing. And if you remember how to graph a line, you could say the y-intercept is at 0, the slope is 1, so we go up 1, right 1, up 1, right 1, or you can use your table, -2, -2, -1, -1, oops, that point is wrong, and all the way up. We connect our points, and we have this line here. Okay, so what's our x-intercept? It's at 0, 0. What is our y-intercept? It crosses the y-axis also at the origin, so 0, 0. If we talk about our domain, in set notation, x is what values and y is what values. So x is going all the way forever. Oh, man, I keep messing this up. So looking at the domain, we going to the left forever and to the right forever again. So set notation is going to be all real numbers. And then interval notation, to the left forever is -infinity. To the right forever is positive infinity. Then for the range, the same thing happens. It goes down forever and up forever. So that's all real numbers in set notation, or in interval notation, it's from -infinity to positive infinity. For most of class, I use interval notation, but if you guys choose to use set notation, that is fine, but you need to recognize both. All right, then let's talk about end behavior. So as x goes to -infinity, what is y doing? And as x goes to positive infinity, what is y doing? So going in the negative direction, y is also going in the negative direction forever. And x goes in the positive direction, y is also going in the positive direction forever. All right, quadratic function. Quadratic function is another one you should be familiar with. F of x equals x squared. So we are, and if you remember, it looks like a parabola or a U-shaped graph. X squared means we're squaring. So -2 squared is a +4. -1 squared is a +1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. And when we plot those, we have -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Okay, for our intercept, it crosses the x-axis at 0, the origin, which happens most of the time with our parent functions. The y-intercept is also at the origin. For our domain and range. So domain, going left to right. How far to the left does this go? This arrow tells me it keeps going, and it keeps going to the left. So again, to negative infinity. How far to the right does it go? The arrow tells me that it keeps going to the right forever. So positive infinity. So for interval notation, again, negative infinity to positive infinity. Or in set notation, all real numbers, the range will be a little different. So how far down does this graph go? We're looking up and down for range. How far down does this graph go? Well, it doesn't go any further than 0 on the y-axis. So the range is from 0, and then it goes all the way up forever to positive infinity. 0 is a point on our graph, so we use a square bracket. Infinity is not really an actual number, so we put parentheses. And then in set notation, it's going to be y. I'll get into the groove, I promise. Y is, for set notation, it's going to be y, all y values greater than or equal to 0. So y is greater than or equal to 0. Now let's talk about the end behavior for our quadratic function. So as x goes to the left and as x goes to the right, so as x goes in the negative direction to the left, in the y direction, it's going up, and up is positive infinity, right? So positive infinity. And as x goes to the right, or the positive direction, y is also going up to positive infinity. Moving on to the absolute value function. If you remember, the absolute value is the distance from 0. And when you measure something, you are always measuring a positive number. So the function for absolute value, I hope you remember that it's the bars around the x. So what is the absolute value of -6? That would be a positive 6. -2 is 2 units from 0. 0 is 0 units from 0. 2 is 2 units from 0. And 6 is 6 units from 0. So when you graph this, -1, 1, -2, 2, we get something that looks like a V. All right, so x-intercept, again, the origin. Y-intercept, also the origin. If we talk about the domain, x values going from left to right, to the left to negative infinity, to the right to positive infinity. There's no holes or breaks, so still all real numbers. The range, how far down on the y-axis does it go? 0. Again, that's a bracket. And then how far up does it go? Well, it goes up forever to positive infinity. So looking at the end behavior, what is the x doing? As x goes to the left, what is the y doing? As x goes to the right, what is y doing? So as x goes to the left, our graph is going upward towards positive infinity. And as x goes to the right, our graph is going upward to positive infinity. Looking at the exponential function is something to the power of x. We're going to focus on the base of 2. So it's 2, the x is in the exponent. So if we're looking at 2 to the negative 2 power, hopefully you remember a negative exponent means we have to take the reciprocal. So that is 1 over 2 squared. Then 2 squared is 4, so 2 to the negative 2 power is 1/4. You also have calculators, so you can use a calculator if you need to. Here we have 2 to the negative 1 power. So again, a negative exponent means we move that to the denominator, make that exponent positive. 2 to the first power is just 2, so 1/2 is that one. 0, 2 to the 0 power. You can plug this in your calculator, but anything to the 0 power is just 1. Then we have 2 to the first power, which is simple, it's just 2, and 2 squared is 4. So I'm going to start in the center, 0, 1, 1, 2, and 2, 4. Okay, and I'm going to show you how this goes up, and it gets bigger and bigger really fast. Here, we're getting smaller, right? So we go to 1/2, so negative 1, 1/2, so that's halfway. Negative 2, 1/4, so that's half of that. So we're halving each time. Half of 4 is 2, half of 2 is 1, half of 1 is a half of 2. We're halving each time. So this is something very important, because if we're taking a half each time, then that means every single time there's a half left over, which means we can never get to 0. So while this line will look like it's going to 0, we will never cross that x-axis. We will never make it to 0. And that, while we're talking about it, is something special that you may have never heard of called an asymptote. So we have a horizontal asymptote at y equals 0, because our graph will never cross that line. Okay, going back to x-intercept, it crosses the x-axis, well, never. We just said it would never reach the x-axis, so there's no x-intercept. And then for the y-intercept, it crosses at 0, 1. And then we'll go on down to the end behavior. So as x goes to the left, or negative infinity, what is y doing? As x goes to the right, or positive infinity, what is y doing? So let's start with the positive one to the right. As x goes to the right, it's very obvious that the y is getting larger and it's going up to positive infinity. What about as we go to the left, or negative? If we go in the negative direction, as we said earlier, that graph is getting very close to 0, but it's not going to reach 0, but our y is approaching 0. All right. So what's our domain? Well, it goes forever to the left. It goes forever to the right. So it's still all real numbers, or negative infinity to positive infinity. What about the range? So it's going downward to 0. No, it's never going to reach 0, but it gets so close to 0, we're going to have to say 0. But we'll use parentheses here, because again, 0 is never going to be a point on our graph. How about how far it goes up? Again, it's going upwards to infinity. Okay, cubic function. That means something that's cubed. So x cubed. So it's negative 2 cubed. Negative 2 times negative 2 is positive 4, times negative 2 again is going to be negative 8. Negative 1 times negative 1 is 1, times negative 1 is negative 1. 0 times itself however many times is 0. 1 to the third is 1, and 2 times 2 times 2 is positive 8. So what does this one look like? If we have negative 2, negative 8, and as you'll see, my graph is actually not big enough, but it's down here somewhere. Negative 1, negative 1, 0, 0, 1, 1, and then 2, 8 is going to be up here. So this is what a cubic function will look like, something like this. All right, so where does it cross the x-axis? At the origin. Where does it cross the y-axis? The origin. What's our domain? Well, keeps on going to the left forever, keeps on going to the right forever, because remember, domain is the x values, so we're only looking left to right. Range is the y values, which is up and down. So how far down? Forever. How far up? Forever. So both of these is going to be all real numbers, or negative infinity to positive infinity. Oops. And then the end behavior. So as x goes in the negative direction, well, the y is going in the negative direction also. As x goes in the positive direction, y is going in the positive direction also. Square root function. Well, pretty straightforward. It is taking the square root of something. So I hope you noticed for my table, I picked perfect squares, so it would be nice and easy. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. And the square root of 16 is 4. Now, how about the square root of negative 1? You have to think, can you square something and get a negative number? Like what two things? If you do a negative times a negative, you get a positive. If you do a positive times a positive, you get a positive. So can we square something and ever get a negative? We can't. So this one is an interesting function because we won't go past 0, 0 for this one. So 0, 0 is an actual endpoint. Then we have 1, 1, and we have 2, 4. 4, 2. And then we have 9, 3, and then it just keeps on going like this. So what's our x-intercept? Origin, 0, 0. Y-intercept also at the origin. Then for our domain and range. So domain is x values. How far to the left does this go? 0. It doesn't go any further than 0. And how far to the right does it go? Infinity or forever. So the domain in set notation would be x values greater than or equal to 0. In interval notation, it would be from 0 to positive infinity. For the range, how far down does it go? 0. How far up? Does keep going up, not quickly, but it does keep going up. So it goes up in the positive direction. So this is all y values greater than or equal to 0 or from 0 to positive infinity. The end behavior on this one is a little different because as x goes to the left, it doesn't go to infinity. It just goes to 0. It doesn't go any further. And then as x goes to positive infinity, because it does keep going forever. So as x goes to 0, y also goes to 0. And as x goes to positive infinity, y also goes to positive infinity. So we just talked about the cubic function. Now we're talking about the cube root function. This is when we're taking not the square root, but the cube root, that is a 3, the cube root of a number. All right, so what number times itself 3 times will give us -8? Well, we just said earlier, -2 times -2 times -2 is -8. So -2, the cubed root of -1 is -1. Cubed root of 0 is 0. Cubed root of 1 is 1. And the cubed root of 8 is 2. So, sorry for the blurry picture, but if you notice, this is the cubic function, and the cube root function is just the reverse, the inverse, the flip-flop of that one. So, back on track. If I graph this one, I go to -8, which is off my screen, -2, it's off my coordinate plane. -1, -1, 0, 0, 1, 1, and positive 8, positive 2. So somewhere over here. So again, it looks like the cubic function, but it's rotated. So where's our x-intercept? Still at the origin. Y-intercept, still at the origin. And the end behavior, as x goes to the left or in the negative direction, the y is in the negative direction also. And then as x goes in the positive direction, the y goes in the positive direction. So the domain, how far to the left does it go? Negative infinity. How far to the right does it go? Negative infinity. Or all real numbers. Range, how far down does it go? Negative infinity. How far up does it go? Negative infinity. Or all real numbers. Phew, 2 more to go, guys. So next up is the rational function, and it's a little wacky. This is also called the inverse function. Okay, so this one is f of x equals 1 divided by x. All right, so 1 divided by -2 is -1/2. 1 divided by -1 is a positive or a -1. 1 divided by 0. Now we have 1 divided by 0, and that's a tricky one because hopefully you recall you cannot divide by 0. It is undefined at that. So we're going to write undefined. 1 divided by 1 is 1, and 1 divided by 2 is 1/2. So this one looks strange, and we will do a whole unit on these rational functions.
Especially you have a visitor in the front office, please.
But for now, you need to know that this is what it looks like. So -2, -1/2, and -1, -1. I know this may not make sense to you guys right now, but again, you will understand it more later. Right now, we're just getting the idea of these parent functions. And then 1, Okay. So this is what the parent rational function or inverse function looks like when graphed. And you may notice or have an idea that we're going to have asymptotes this time also. I mean, one hint is the fact that I put it on the paper. But another hint is that if you look, the x-axis, I've specifically drawn my graph because it will never touch the x-axis here. And this function will also never touch or reach the y-axis. So we have a horizontal asymptote at x equals 0. Y equals 0. This is this line this way is at y equals 0. And then we have a vertical asymptote. So vertical is going this way, and it goes through x equals 0. For the domain, well, what are our x values? Our x values go to the left forever and to the right forever except for 0. So the domain in set notation is going to be x is not equal to 0. So that says all x values except 0. To write the domain in interval notation, what we have to notice is that we have two pieces. So we're going to have two intervals that we're going to have to write. So this part of the graph goes to the left forever to negative infinity, but to the right, it stops at 0. So from negative infinity to 0, and 0 is not a point on the graph, so we use parentheses. This side goes from 0 here all the way to positive infinity. And we put these together or connect them with this U that symbolizes the union. Okay, range is going to be similar. So all y values, it goes down forever, it goes up forever, except for 0. So it's all y values except for 0. And then again, same for interval notation. It goes down to negative infinity. It comes up to 0 and stops. Then there's a little space, and from 0, it goes up to positive infinity. Oh, and I skipped x-intercepts and y-intercepts. Where does it cross the x-axis? It doesn't. Where does it cross the y-axis? It doesn't. And then our end behavior. So what you have to remember about end behavior is that we're talking about the ends. As x goes to negative infinity and as y goes to negative infinity. We're not talking about all the gobbledygook in the middle. So as x goes to negative infinity, what is y doing? As we go this way, y is approaching 0. It's going up to 0. Won't cross it, but it's going up to 0. And then as x goes to the right or positive infinity, y is going in the downward direction towards 0 here also. Okay, last one and kind of the weirdest one is the greatest integer function. So we have this funky looking, well, it depends on, you could just use regular brackets, but it's brackets around an x. This is also called the step function or the floor function. And what it is, it finds the closest, I feel like there has to be a definition because it's very strange. The closest integer to x without going over, okay? So that's the weird part. Okay? So if I'm looking at my x's here, -5, the closest integer to x is actually -5. The closest integer to -3.2 without going over is -3. Remember, integers are positive and negative whole numbers. The closest integer to 0.7 is going to be 0, because if you round this to 1 correctly, would be 1, but 1 is over. So you have to go down to the integer below it, which is 0. So this greatest integer always causes me concerns, because we're not going to the, doesn't seem like we're going to the greatest. We're going smaller. 2.3, the greatest integer without going over is 2, and then 5 here. So what does this look like? Graphing is a little strange also. So let's just go here with the -5. So when x is -5, the greatest integer is itself, -5. If I go to -5.5, which is, I know it's not over here, sorry, this is -4.5, we're still using -5. If I go to -4.25, we're still using 5. But when I get to -4, the greatest integer is going to be 4. So I'm going to jump up to that. So this is how the graph ends up looking. So it's -5 all the way till we jump up to 4, then, or -4. Then we go to jump up to -3. Then we jump up to -2, and so on. So I always have issue that it's actually the lower number, but it's called the greatest integer function. Okay, you get the idea. So what's our x-intercept here? Well, it's still 0, 0. And our y-intercept is still 0, 0. The domain. So if we look, and this does keep on going, even though I stopped, it keeps on going forever. So it does go to the left forever, and it does go to the right forever. And these gaps are not concerning us, because we go -5 and then -4 and then -3. So we are covering everything. Everything is covered as far as the domain. So it's actually all real numbers, or -infinity to +infinity. The range is kind of weird, so we'll just put all integers. If you look, it jumps from -5 to -4 to -3 to -2. So when you look vertically up and down, there's nothing in between. So it has to be all integers. Now, in behavior, again, remember it's end behavior. So we're not talking about all the stuff in the middle. At the end, when x is going towards -infinity, what is y doing? Well, x is still going on forever to -infinity, and so is our y going to -infinity. What is x doing as far as going to +infinity? Well, even though I quit graphing, it does keep going. We can keep plugging in x's. So it does keep going to +infinity, and y also keeps going towards +infinity. And now we have a full booklet of our parent functions.